let me get that started. All right, so thanks everyone. Sarah Allred will be talking about unavoidable induced subgraphs of large two connected graphs. Thanks.
Get it where I can see everybody. All right, so like she said, I'm going to talk about induced subgraphs. So the first thing I want to be able to do is define what is an induced subgraph. So with induced subgraphs, the only operation we are allowed to make this graph smaller is to delete vertices. So if I want to delete this red vertex, what I need to do is also delete these blue edges. So when I remove the red vertex, I'm also removing all 3 blue edges. I cannot remove just 2 of them. And so I will get this as an induced subgraph. If I want to get another induced subgraph of this graph, I can remove this red vertex and then these 2 blue edges that are touching that red vertex and get this graph as a result. So notice here I removed 2 vertices and I broke the graph into 2 pieces. Thinking about 2 connected graphs, that's what we're wanting. We removed 1 vertex, the graph is still going to be in 1 piece. We need to have a set of 2 vertices that we remove. All right, so then that gets us to kind of the motivation for what we're doing. So Ramseys' theorem says there is a function f such that every graph on f of r vertices contains an induced complete graph or complement of a complete graph. We're going to think of R as our target order. So what we're going to think about a theorem of this type like is that every giant graph contains a large induced complete graph or complement of a complete graph. So every theorem from here on out is going to be phrased in this giant large type way, where large is our target order, but in the paper, it's some function on some variable of vertices. Okay, so we have here no restriction on the connectivity of the graph. All we know is that the graph is really, really big. If we restrict the graph to being really, really big and connected, then we get that every giant connected graph contains a large induced complete graph, a star, or a path. Now this giant connected graph would also contain the complete graph and complement of a complete graph, but for these type of theorems, we want our list of large graphs to match the connectivity that we have in our assumption. So we're assuming the graph is connected, so we want our large graphs to also be connected. All right, so the next kind of step is, well, we move up our connectivity to 2. When the connectivity is moved to 2, we have to weaken the relationship to topological minors. So every giant 2-connected graph contains a large topological minor isomorphic to K2R or a cycle. Now, in a topological minor, why this is a weaker operation is because we can delete edges, we can delete isolated vertices, and if we have 2 or more edges in series, then we can replace that with a single edge. So just by being allowed to delete edges, we have a significantly weaker relationship because in induced subgraphs, we can only delete vertices. So then the next kind of question was, well, if we keep this topological minor relationship, can we say anything about 3 connected graphs? Operovsky, Oxley, and Thomas proved that every giant 3-connected graph contains a large topological minor isomorphic to a wheel, K3R, and a ladder-like graph like we have here. So we think of a ladder, we can kind of pinch the ends and join it with an edge to have a 3-connected graph. They also proved it for a type of 4 connectivity, but that's a longer list of graphs and a bit more complicated. So next, we can think about another relationship called parallel minors. A parallel minor of a graph G is obtained by contracting some edges, deleting some isolated vertices, and replacing two or more edges in parallel with a single edge. This operation is a dual notion to topological minors, which is why it's of some importance to these type of results. So we have topological minor results. If we can have parallel minor results, then that could give us hope that, hey, maybe there's some matroid type result. And because LSU, the hope of matroid results is kind of appealing. All right, so for parallel minors, Carolyn, Chun, Ding, Operovsky, and Bertigan proved some results. First, for every giant connected graph contains a large parallel minor isomorphic to a star, a big cycle, a long path, or a complete graph. For two connected graphs, they got that every giant two connected graph contains a large parallel minor isomorphic to K2R plus, which is K2R, but we have an edge between the two vertices of degree R, a cycle, a fan, and a complete graph. They also proved it for three connected graphs. So every giant three connected graph contains a large parallel minor isomorphic to one of what we're calling K3 triangle or K3R triangle. That's K3R, but in our bipartition of size 3, we have a triangle joining those three vertices, a wheel, a double fan, and a complete graph. So here are three results for parallel minors. We had similar results for topological minors. So that means we would expect a matroid result. Now notice this is in 2009, but in 1996, they proved first for binary matroids that every giant three connected binary matroid contains a large minor isomorphic to one of those four matroids. And then they generalized it from binary matroids to every giant matroid contains, or every giant three connected matroid contains a large minor isomorphic to one of this list of matroids. So this, James, is for you as my obligatory matroid thing since I am from LSU.
So tell me what SN is then.
It's a binary spike.
The binary spike. Thank you. Okay.
Does that make you happy, James?
Thank you, Sarah.
All right, I am not a matroid theorist. I am a graph theorist. So the rest of this talk is graph theory, not matroids. So if matroids aren't your thing, we're going to be going into graphs. So our question was, well, what if we drop back to two connected graphs and we want to think about Ramseys' original relation of induced subgraphs? What can we say about that? It turns out that we can prove that every giant two connected graph contains one of the following: a large complete graph, a member of the family script K2R, K2R plus, and CL. A CL is a clean ladder as an induced subgraph. So some of these things are new. So I will give you the graphs here. A complete graph, we're talking about induced subgraphs. So any vertex that we delete is going to give us a smaller complete graph. So in our giant two connected graph, when we find a complete graph that's large enough, we're going to be happy. All right. And the next one, our family K2R, is the complete bipartite graph K2R, where the edges may be subdivided a finite number of times. So notice that in the K2R, the edges are a little bit thicker than the edges in KR. Anytime in this talk you see edges that are thicker, that means it could be a path, whereas thinner edges are definitely just a single edge. And because we're talking about induced subgraphs, there's nothing we can do to delete one edge that would join members over here, right, of the bipartition with degree R. The only thing we would be able to do is delete one of the endpoints, but we don't want to delete one of the endpoints because we still want to keep our structure of K2R. So we have to be happy with K2R, but having that edge. And again, in this family, things can be subdivided any number of times because we can't do any type of contraction to make those paths be single edges. The last structure is what we're calling a clean ladder. And here, if you're familiar with two connected graphs, you may have been expecting a couple of families in our list. You may have been expecting a fan in the list, and notice that we have a fan here. So we have some vertex in red that has a bunch of rungs, and then on the bottom, we have the rail of the ladder where we could have it be subdivided. So if this red structure has at least R vertices, which is our target order, then this is a special case of a clean ladder of our target order. So we're good. In fact, if we have a clean ladder that is bigger than our target order, we're also going to be satisfied with a clean ladder that is bigger than R. So here, if we find some sort of fan structure that has at least R vertices, then we're going to be happy. All right, the next thing you would expect is you would expect a cycle to be in this list. Notice that here we have a blue cycle. It is not a 4 cycle because the top and bottom edges are thicker, so those could be paths. So this cycle could be any size you want. If this cycle happens to have at least R vertices, then it's going to be a special case of a clean ladder, and we're going to be happy with that. So the last feature of a clean ladder that I want you to think about is this green pair of edges that cross. All right, so when we think of a cross, it's just going to be a pair of edges that overlap like this. And notice that on the top and bottom rail between these two edges, those are single edges, okay? We're talking about induced subgraphs, so there's nothing we can do to delete those edges. So if we see some pair of edges that are like this, we're going to have to be happy with them because there's nothing we can really do about it. All right, any questions so far? All right, so for the rest of the talk, what I'm going to do is I'm going to give kind of an overview of how we go about proving this. Okay, we separate this into 2 cases. The first, our graph has a really, really long path. That path doesn't have to be induced. And then if it doesn't have a really, really long path, we can do that because we prove a lemma that says basically we either have in our giant 2 connected graph a really long path, or we have a member of the family K2R and K2R plus. As a reminder, these are the graphs we're looking at. So this lemma says our graph either has a long path or has a member of one of the 2 families in our theorem, in which case we're good. Right, so looking at this case, I'm going to show you how we find the members of these 2 families. The first thing we want to do is, since we have a connected graph, we're going to take a spanning tree of that connected graph. Moreover, we're going to take a normal spanning tree. So for a normal spanning tree, what we have is that any edge that's not this NG, but not on this spanning tree, has to go from a descendant to one of its ancestors. The important thing for us is that means that there are no edges between these vertices below V on the same level or kind of connecting the subtrees here. So that's going to be the way we think about wanting to form our bipartite graph. The first thing we want to think about is this red path. We know that we don't have a really long path because if we have a really long path, then our lemma says we're good. So we know this red path is not too long. We also know that this two-connected graph has a ton of vertices. So since this two-connected graph has a ton of vertices, there's no paths that are really long. That means we have a vertex like V here in red that has a ton of children, right? The number of children is really large relative to the number of vertices above V, right? So since this graph is two connected, we know that V is not a cut vertex. So since V is not a cut vertex, what we know is that edges from the subtrees from the descendants of V, so here we would have 6 subtrees from the children of V. We know each subtree has to have at least one edge to one of the gold vertices above V. We know that because V is not a cut vertex, so there has to be something that goes above V. Otherwise, in our graph, otherwise V would be a cut vertex of the graph. All right, so, and then because there are a lot of children of V, so we have a lot of these subtrees relative to the number of vertices above V, that means there has to be a bunch of edges that go to the same vertex in G. We have 2 cases for that. Either they can go to a vertex that is an ancestor of V that is not adjacent, like we have in this case, in which case we're going to delete every vertex from the ancestor of V, or in between the ancestor of V and V. We can do that because it's an induced subgraph. And then when we do that, we'll get a member of this family, K2R. You can see we have the blue vertices that are in the bipartition of size 2 and the red vertices that are in the bipartition of size R. All right, so the next case we could have is, what if a bunch of the descendants have an edge in G going to a vertex that is an ancestor of V and is adjacent to V? So we're looking at this case. All right, remember we're in induced subgraphs, so we cannot delete the edge between V and its neighbor that is its ancestor. Okay, but that's okay because that'll give us a member of the family K2R plus. So you see our 2 blue vertices with the blue edge and the 3 red vertices. Any questions on this part? So what this tells us is that our giant 2-connected graph either has a really long path, in which case in this lemma we were good, or it gives us a member of one of the 2 families, which means what we have to prove now is what happens if our giant 2-connected graph has a really long path that may not be induced. So there's this theorem of Galvin, Rival, and Sands that says every graph with a really long path contains a large induced complete graph, KRR, or a large induced path. Okay, we're thinking of these paths as having kind of our target order. In this theorem, there's no assumption of connectivity. So what we want to do is we want to take this theorem and massage it a little bit to get it into our case. So in our case, what we can prove is that every 2-connected graph with a really long path contains a large induced complete graph, K2R, or a messy ladder. So if you're comparing these theorems, KR is staying the same. And remember, KR is one of the graphs in our list. So if we find this large KR, then we're satisfied. Now, if you think about the KRR from Galvin, Rival, and Sands, we can take one of the bipartitions of size R, delete all but 2 vertices, which is an allowed operation since we're talking about induced subgraphs, and get K2R. K2R is a member of our family script K2R, where no edges are subdivided. So the biggest difference here is that we're saying when you have a two connected graph, the long induced path becomes a structure that we're calling a messy ladder. So this messy ladder has a ladder type structure. So we have an induced path that forms a rail on the top, an induced path that forms a rail on the bottom. The only structure to the rungs that we have is that there has to be a rung joining the first vertex of the red path to the first vertex of the blue path, and joining the the last vertex of the red path to the last vertex of the blue path. Every other rung can go anywhere, provided it goes from the top red rail to the bottom blue rail. So there's no real kind of control we can have at this point for the messy ladder, other than it goes from the top to the bottom, and it looks really messy. So that's why we called it a messy ladder. All right, so the next thing that I'm going to talk about is kind of a general overview of how we took a long induced path and we got a large messy ladder. In order to do that, I am going to need a concept that's called Tut bridges, because bridges already, for a graph theorist that has no connection to Tut, has a definition already. I'm making sure to let you know we're referring to the Tut version, which y'all are at Waterloo, assuming. So that's the version y'all are probably a little bit happier with. Tut is my academic great-grandfather, so it's a version of bridges that I also use. And because it's a Tut definition, if I had tried to write it out in words, we would be here all day trying to figure it out. All right, so we're going to think about it with this picture. Here, we're going to think about this gold graph. All right, we're going to think about the bridges of this gold graph. To do that, we think about deleting this gold graph, not in a graph theory sense, but in a topological sense. So when we delete this gold graph, the black edges are still just kind of hanging out there in space, and we'll break into three different pieces. So you see we can have a red piece, a blue piece, and a green piece. And then when we put back in our gold graph, we're going to see that we have three bridges. In this case, a red bridge, a blue bridge, and a green bridge. Okay? Good so far? All right, so how we use this is we take our induced path that is really, really long, and we find the bridges of this induced path. Okay, here we put 6 bridges. There may be many more bridges of this path that aren't pictured here. We're taking these 6, right? In each bridge, we're looking at an induced path. So Q1 is an induced path in our bridge B1 that we have both endpoints on P. All right, and we do that for each of the 6. We know that these bridges overlap in this kind of manner because our graph is too connected. All right, if the bridges didn't overlap, then we would have been able to find a cut vertex. So we know we have some sort of set of overlapping bridges, and we want this kind of structure of overlapping bridges so we can delete any other bridge that isn't here by deleting the vertices of those bridges. All right, we also know that every path Q has at least one vertex. It has to have at least one vertex because our path VP is induced. So if Q was just a single edge, then our path is not induced. All right, so if we look at Q1, if in G there happened to be some path from Q1 to P, we can just delete the internal vertices of that path and be looking at a graph like this. Okay, so what we're assuming now is that what we see here are all of the vertices that we have to deal with. Okay, the next thing we're going to think about is this red path. All right, this red segment goes from the beginning of Q1 to the end of Q1 on P. If this red segment has enough vertices, right? If this red segment has our target order, then what happens is Q1 and this red part of the path P is going to give us a messy ladder. All right, so that means we can assume on P that none of the Qs go too far, right? If any one of them go too far, then we're going to get an induced messy ladder from that bridge. So we have a really long path. None of our paths Q go too far. That tells us we have a lot of these bridges and then a lot of the induced paths in the bridge. Or sorry, induced paths in the bridges. So here I have 6, but there may be many, many more because the path may be really long. 6 is just kind of an easier number to draw. The next thing we're going to do is I am going to redraw this graph like this. So what happened is I moved every other Q and that bridge just down. So now we can kind of start to see there may be some type of ladder structure here. The graph is exactly the same. It's just now in an easier form to look at. Okay. So remember, the only thing we can do to make this graph smaller and try to find a messy ladder is delete vertices. So what we're going to do is we're going to look at the segments on P where our Qs overlap. So here we have 4 red segments and 1 gold segment. Notice that the 4 red segments are thicker, so they are paths. Therefore, there are internal vertices on those red segments that we can delete. The gold segment is thinner. It is a single edge. We cannot delete a single edge. So that gold segment is going to have to stay. Okay, so our step, we delete the internal vertices of the red paths. We can't do anything with the gold edge. It stays. And we're going to have a messy ladder. You can see on top, we have the red rail that goes almost all the way to the end, but we have that little black segment. That's our last rung. And then blue, we start with a little black segment. That's our first rung. And we go all the way to the end. All right. Any questions on the long path to messy ladder? All right, so now remember in the theorem, we didn't have a messy ladder. We had a ladder that we had imposed a lot of structure on. So the next thing we need to do is we need to figure out how can I take the messy ladder here and clean it up. All right, the first thing I want to think about is if I look at the top 3 graphs, so KR, K2R, K plus 2R, if I have any of these in my messy ladder for any reason, then I'm happy, right? Those 3 are in our list, so we're good. So we know those aren't there. Now remember the last 2, if they were big enough, were special cases of our clean ladder. So that allows us to make a first kind of run at cleaning up this ladder. So what I want you to notice that if this vertex here has a bunch of rungs that it's adjacent to, or incident with, sorry, then what we get is an induced fan. If this fan is large enough, so if it has our target order, we want a clean ladder of order at least R. So if this fan here in red has order at least R, then we're good. Right, we've found a clean ladder of order R. That allows us to bound the degree. The next thing we want to look at is, say we have this blue vertex, and you can see it is incident with 2 rails. And then on the bottom, the red is the part of the rail that is covered by those 2 edges. All right. So if this red segment is really, really long, right? If this red segment has at least our target order, then we get an induced cycle here, and we're going to have a clean ladder. So that allows us to bound how far we can go between 2 rungs that are incident with the same vertex. All right. If this happened to have like another vertex or another edge kind of here, we can do the same type thing, but we divide it into 2 pieces. Okay, so that allows us to bound that distance. There's another way that we can get a cycle. All right, if we look at 2 consecutive rungs, so here on this red segment, there are no other rungs. If this red segment has close enough to our target order, then what we're going to get is an induced cycle here. All right, so if we see an induced cycle like this of our target order, then we have found a clean ladder of at least our target order, and we're good. All right, so that's kind of our first run at cleaning it up, is we are limiting the size of the fans and limiting the size of induced cycles. All right, everybody good? The next thing we want to do to clean it up is we want to think about how edges cross. So here we have 4 what we're calling crosses, right? So just a pair of edges that cross. And we have a little bit more than that. The first thing we want for each of these crosses is that they are not contained inside some larger cross. So if you look, the 3 red crosses are not contained inside some larger cross. All right, we want them to not be completely inside. If you look at this first gold cross, however, it is contained completely inside this red cross. So the first gold cross is one we would not want to pick because it's completely contained inside another cross. So we want to pick crosses that are as big as possible, as far as not being inside some other, right? So we're trying to make the distance here on the rails, we refer to it as the span, but span can have other contexts in matroid theory. So try not to use that quite as much. But basically we want this here to be as big as possible. All right, so we're going to be thinking about these 4 crosses that are not contained inside some other cross. The next thing we want with these 4 is we don't want them to overlap edges, okay? We want these crosses to be separate as far as edges. If they overlap vertices at the ends, that is fine. So notice on the 3rd and 4th cross, they overlap at that one top vertex. That is allowed. We can touch at vertices, we cannot overlap edges. So those are the things we're wanting for our crosses. And then we want to take a maximal sequence of these type of crosses. All right, so we want to have a maximal sequence where we can add no more of these types of cross. All right. Now that we have this maximal sequence of non-overlapping crosses that go as far as possible, we're going to look at these blue segments, which is the pieces of our rails that are in between the cross. And we know because we don't have large fans and we don't have large induced cycles, that these blue segments cannot be too long. All right, so we've limited the size of the blue segments. The next thing we can limit is the size of these gold segments. All right, when we're thinking about limiting these, we're not thinking about limiting it on just one rail, but kind of a combined between the top and bottom rail in between each cross. So we're looking at the top and bottom for the first cross. So from the first rung to our first cross, the top and bottom from the first cross to the second, and so on. We're looking at just those little pieces. If that little piece is big enough, then what we have is a clean ladder, because we've said we have a maximal sequence of these kind of crosses. So there are no crosses where all 4 vertices are in one of these gold things, right? Because we could not fit any more crosses on here, right? So we know that that has no crosses, which means it's going to be a clean ladder. All right, kind of makes sense. Now notice between the gold and the blue, we partitioned the rails. So we've limited the order of the gaps and the order between in each cross, right? So since we've done that, and we know that this messy ladder is really, really big, and our gaps are not that big, that means we have a lot of these crosses, okay? Having a lot of these crosses is the most important thing to guarantee a clean ladder of the size that we want, or sorry, of the order that we want. Because each of these crosses is going to contribute at least 2 vertices to our clean ladder, okay? So we've taken a messy ladder, we've started the process of cleaning it up. The assumptions that we have at this point is we have a maximal sequence of crosses that don't overlap edges and are not contained inside some other cross. The next thing we want to do is we want to figure out how to resolve the crosses that we can in this sequence. All right. So here we've moved to more of a schematic type graph. We're going to assume that we do have a maximal sequence here. So there are no other crosses of the type that we want that can be placed here. But it could be edges, right, that go in but be there, but don't cross. Right? So we may just have kind of vertical edges, or like in the first case, having a fan. Here, I want you to notice we basically have 3 types of crosses. What we have is the first type, where the red rail and the blue rail have edges or have vertices there, right? So they are subdivided. The second type of cross, only one of them has vertices there. The other is a single edge. And then the last type of cross, both of them are single edges, okay? I put a black dot there to really call attention to the fact there are internal vertices there, okay? So the first thing we want to look at is this piece of the graph. We've assumed we have a maximal sequence of the crosses that we want. So we know there are no crosses here. That means this part is already going to be a piece of a clean ladder. So we can fade it out and consider it to be good. The next thing we want to do is we want to resolve this cross, okay? We know that this edge is not going to do anything, because when I resolve the cross, what I'm doing is deleting the vertices in the red rail that are thicker and in the blue rail that are thicker. And that looks like that. So when we do that, notice we got rid of the black rung that was just kind of hanging out there and crossed our cross, but didn't cross anything before. All right. And we know that there are no edges from the left part of our graph that is faded to the right part of our graph that is not, because we would have had a bigger cross. All right. So now we've taken care of anything to the left. There are no crosses. Okay. The next thing we're going to do is we're going to, on the right, move the blue rail to the top and the red to the bottom. So what happens is the edges in our cross become members of the rail, and our cross has now disappeared. Okay. This does not change the graph on the right, right? Our crosses are still going to be the same. The relationships are still the same. Blue is just on top, red's on the bottom. All right, so the next thing we're going to look at is this second type of cross where one of the rails has internal vertices. We're going to do the same type thing and delete those internal vertices. I cannot do anything with the blue edge on top because we're talking about induced subgraphs. So we cannot delete just an edge. And we're wanting to maintain this ladder type structure, so we don't want to delete the endpoints of that edge. All right, so we've deleted internal vertices. We're going to do the same thing where we twist the right-hand side. That doesn't affect the left side of our graph. That's already been cleaned. And we get this. So the rungs that were in our cross became members of the rails, and the blue edge that was a member of the rail is now a rung. All right, so that would be how we can resolve crosses where we can delete vertices. All right, those are the only types of crosses that are really going to affect anything, as you can see with this last type of cross. All right, I cannot delete the blue edge because it's just an edge and we're looking at induced subgraphs. I cannot delete the red edge because we're looking at induced subgraphs. All right, but if for some reason I still wanted to apply the process where I flip to the right-hand side, I can do that. But notice I'm getting the same graph, just our black rungs became members of the rail and our red and blue members of the rails became rungs, and then to the right, we flipped. All right, so since we're looking at induced subgraphs, there's nothing I can do to get rid of a cross of this type, okay? So our process of resolving the crosses is going to give us a clean ladder. It doesn't matter how big the ladder is. We know at this point it has to be clean. That is the reason we really want to have a lot of crosses. So if we know we have a lot of crosses and we're doing this resolving process a lot of times, and each time we know we're going to have at least 2 vertices in our clean ladder from that process, that's how we're making sure that we get a clean ladder that is of at least our target order. All right, so if we couldn't guarantee that there was a lot of crosses, then yeah, we have a clean ladder here, but this clean ladder may not be big enough. All right, any questions on that part? Okay. So as a reminder, it's been a while. The theorem that we prove is that every giant 2-connected graph contains one of the following: a large complete graph, a member of the family K2R, K2R plus, or a clean ladder as an induced subgraph. And we took an approach, either the graph has a really long path or it doesn't, and followed our path, followed our trails kind of based on those 2 things. Our next step is we're working on taking this graph or this result and thinking about what happens in infinite graphs. There's still a decent amount of work left to do there, but I think we're on probably the right track. And yeah, that's what I got. Thank you.
Thank you, Sarah. I like to do applause at the end, so let me ask everyone to unmute themselves first. All right, and let's give Sarah a round of applause. All right, are there any questions? You can just speak out. I've got one to get us started, which is that all of these problems seem really hard in the 3-connected case, right? Because you can't look at subdivisions. But I'm wondering if there are any results that sort of say explicitly how hard it is. Like I think, for instance, that you get from your results that there are only finitely many minimal hereditary classes which are 2-connected. So I'm wondering if there are any counterexamples of this sort of thing for higher connectivities.
I have not looked much at higher connectivities because just 3 connected for topological minors was really, really difficult. And so 3 connected for this is going to also be pretty difficult. So that's not a place that I have looked with my research, but it would be an interesting place to try to go. It would just be pretty difficult.
Yeah, it seems hard. I wonder if there's a way of like sort of saying why it's hard.
Yeah, I mean, the really hard thing about induced subgraphs is with a lot of these other results, we can make our class smaller, right, by being able to delete edges, right? So we can eliminate fans that you would think because we can delete edges in there and get a cycle. But not being able to delete edges really is kind of the hardest thing at first for me to wrap my head around. Because I was like, oh, wait, we can just get this one thing. Nope, Sarah, you deleted an edge.
Right, yeah.
Yeah.
Are
So
there any
in
other,
in the direction of Rosa's question, so a weaker thing than being 3 connected would be to have a large set of vertices in your graph that you can't disconnect any 2 of them by deleting 2 vertices. And so it might be like you have a lot more freedom if you want to find an induced subgraph that's got a large 3 connected set of vertices, subset of the vertices. And that might be more similar to the kinds of things you're doing than going straight to 3 connected, because I suspect that, like what Rose was asking, there may well be negative results about 3 connectivity that you don't have nice answers, but this question probably has a nice answer.
Okay.
And it also might be like a partial thing on all. There are similar things like this for minors, so that there is a theorem of Benson, Joris, and myself to do with having a large K-connected set of vertices and minors, and it implies the grid theorem. And there are nice conjectures about induced subgraphs and branch width, and this might be one way at approaching those conjectures.
Okay.
are there any other questions? Yeah.
Do you hear me?
Yes.
So maybe this was answered at the beginning of your talk. I was late. Sorry for that. But did you think of application of this? I mean, to other open questions, sky-boundedness, or?
I have not thought about applications of this into other things. I was just kind of more focused on proving this kind of structural result rather than looking at the application, but would be interested in thinking about some of the applications into other areas. I know that our numbers are really, really large because we depend on Ramsey's theorem. So because we're depending on Ramsey numbers, that already makes things pretty crazy large, which I don't know if that'll help any in applications.
Well, you have question where is this bounded by some functions, and it can be an open question, so you don't care really for the bound. So there might still be applications. So.
Yeah. So for us, we were our numbers are by no means best possible. We were thinking about this in terms of an existence result, as opposed to making our bounds really, really tight. So some of our assumptions that we made were made in terms of that with the numbers. So like from the first one with our long path, you could get a long path in the tree by going up and then coming back down. We didn't think about those cases. We just thought going from the top to the bottom, having that long path. So that would be one place that could like tighten our numbers, and then that could help to make functions. I think that's kind of along your lines. I haven't thought much ever about chi-boundedness though.
Yeah, I'm curious if you have any particular applications in mind. Nicola.
Do I? No, I didn't think of a particular application. Yeah, okay. Is this written somewhere? Is there a preprint or?
Yes, it is on the archive.
Okay, thank you.
And in that, obviously, we do calculate out all of the numbers. So instead of giant and large, you get exactly how big is giant, how big is large.
Thank you.
All right, well, thank you again, Sarah. I'll go ahead and end the recording. If I can figure out how.